Welcome to the chapter on capacitors. Capacitors are fundamental components in electrical engineering and are widely used in various electronic circuits. In this chapter, we will cover the basics of capacitors, how they charge and discharge, the energy they store, and their application areas. A capacitor is a passive two-terminal electronic component that stores electrical energy in an electric field. It consists of two conductive plates separated by an insulating material called the dielectric. The capacitance of a capacitor is defined as the ratio of the electric charge on each conductor to the potential difference between them. The formula is C equals Q divided by V, where C is the capacitance, Q is the electric charge, and V is the potential difference. The unit of capacitance is the farad, which is defined as 1 coulomb per volt. Consider a parallel plate capacitor with plates of area A and separation D, filled with a dielectric material of permittivity epsilon. The capacitance is given by the formula C equals epsilon times A divided by D. When a voltage source is connected to a capacitor, it starts to charge. The voltage across the capacitor as a function of time is described by the equation V of t equals V0 times 1 minus e to the power of negative t divided by RC, where V0 is the supply voltage, R is the resistance in the circuit, and C is the capacitance. If you connect a 9-volt battery to a 1000 microfarad capacitor through a 1 kiloohm resistor, the voltage across the capacitor after 5 seconds can be calculated as follows. V of t equals 9 times 1 minus e to the power of negative 5 divided by 1000 times 0.001, which is approximately 9 times 1 minus e to the power of negative 5, which is approximately 9 times 1 minus 0.0067, which is approximately 8.94 volts. When a charged capacitor is connected to a resistor, it discharges over time. The voltage across the capacitor during discharge can be described by the formula V of t equals V0 times e to the power of negative t divided by RC, where V0 is the initial voltage across the capacitor, R is the resistance in the circuit, and C is the capacitance. Using the same 1000 microfarad capacitor and 1 kiloohm resistor, if the initial voltage is 9 volts, the voltage after 5 seconds is V of t equals 9 times e to the power of negative 5 divided by 1000 times 0.001, which is approximately 9 times e to the power of negative 5, which is approximately 9 times 0.067, which is approximately 0.06 volts. The energy stored in a capacitor is given by the formula W equals 1/2 times C times V squared, where C is the capacitance and V is the voltage across the capacitor. For a 1000 microfarad capacitor charged to 9 volts, the stored energy is W equals 1/2 times 1000 times 10 to the power of negative 6 times 9 squared, which is 0.5 times 0.001 times 81, which equals 0.0405 joules. Capacitors are used in various applications, including energy storage, filtering, timing circuits, signal processing, and power factor correction. They can store and release energy quickly, smooth out voltage fluctuations, create time delays, block direct current while allowing alternating current to pass, and improve power factor in AC power systems. In a power supply, capacitors are used to filter out the ripple voltage from the rectified output of an AC to DC converter. This ensures a stable DC voltage for electronic devices. In summary, capacitors store electrical energy in an electric field. We discussed their charging and discharging behavior, the formula for energy storage, and various applications in electronic circuits. This concludes our chapter on capacitors. By understanding the principles and applications of capacitors, you will be better equipped to design and analyze electronic circuits in your future studies and career. Thank you for watching.